Awesome. Thanks for introduction, and thank you again for having me. It's really great pleasure for me to be here. I was checking actually your course page, and I was amazed with the topics you're covering. And I was honestly, when I was looking, I was thinking that I wish I had this course when I was PhD student. Like back then when we were doing, I think machine learning was not as popular as it is now. Yet alone imagine deep learning. I remember I took machine learning, and my professor actually skipped the neural network section, saying these things don't work. So anyway, exciting time to be at. Denoising diffusion models, I believe maybe they're going to be the generative learning champions of maybe early 2020s, and we will see how long they're going to last. So I'm pretty sure you actually covered, I saw in your course, you're covering many different frameworks for deep generative learning. Maybe just a quick recap. In deep generative learning, we assume that we have access to some set of samples drawn from unknown distribution. For example, here, the set of samples represents set of images from some cute cats. And we're going to use these images to train a deep generative model, right? If everything goes smoothly at the test time, at the sampling time, we want to now use this deep generative model and draw new instances. And hopefully, if our deep generative model has been trained properly, these instances would look like the training distribution, samples from training distribution that we use for training. So if we use cute cats, the goal is to generate cute cats eventually. So this is the ultimate goal, and I'm going to come back to it eventually again. So if you're familiar a little bit with deep generative learning, this landscape of deep generative learning is filled with a variety of frameworks. Generative adversarial networks were very popular for a very long time, especially for in image generation, computer vision community. Beyond them, we had variational autoencoders, autoregressive models, normalizing flows, energy-based models. And these days, there is a new key player in this arena called Denoising Diffusion models that today I'm going to try to briefly introduce you to these models and maybe create a case that these models actually do very well, perform very well for deep generative learning, and they're going to probably be around for a while. As I mentioned, the Denoising diffusion models are emerging as powerful generative models. They're even outperforming generative adversarial networks on some challenging data sets such as ImageNet. Here, I'm showing you two example works, one from OpenAI on the left side and one from Google on the right side, where researchers showed that by training diffusion models on challenging data sets such as ImageNet, you can generate very high quality diverse images on the categories that are present at in the ImageNet data set. Almost the same groups at OpenAI and Google, a year later, fast forward 1 year later, they showed that actually similarly, denoising diffusion models can be used also for training text-to-image generative models. If you're present at social media, it's probably very hard for you. It was very hard for you to not notice a lot of excitement around these models. DALL-E 2 and Imagine are examples of really powerful models, one from OpenAI, one from Google, where these frameworks can take a text and generate image that corresponds to text. And the quality of the images that are coming from these models is amazing. Like you can for example, Imagine can create this scene where teddy bears are celebrating their co-worker's birthday, where the cake looks like pizza. To me, as someone who has been around, has been working on generative learning for maybe 5-6 years, this was a dream actually for a lot of practitioners to be able to get to a point where we can build generative models that can do this well. And I think it's not exaggeration to say that every day I'm working on these models, I'm kind of living my dream, like these things were out of reach for previous frameworks. So today, I'm going to try to start with a very, very brief introduction of diffusion models, and I'm going to highlight a few recent projects that we've been doing at NVIDIA. After that, I'm going to try to dive a bit deeper and discuss the sampling challenges from diffusion models and present maybe 3 example works that we have done. One is called latent score-based generative models, which are also known as latent diffusion models in the community, denoising diffusion GANs, and higher order solvers. These are 3 example works that I will discuss deeper. And by the way, as Sawyer said, please feel free to stop me, ask me questions. If I feel that we're going to fall behind our time schedule, I will say maybe we can defer some of the questions to the end of talk. So let's just start with denoising diffusion models, a brief intro. So denoising diffusion models, they go actually with two names. One is denoising diffusion models, or sometimes diffusion models for short, but they're also known as score-based generative models. These two are almost the same. They consist of two processes. One, a forward process that here in the bottom, I'm showing you from left to right. The forward process starts from data, this image of cute cat, who happens to be my cat. His name is Peanut. We're going to start with Peanut's picture, and we're going to add gradually noise to his picture, one step at a time. And we're going to keep doing this so many times, such that eventually on the right side, we actually get only white noise. So if you take an image and you keep adding a small Gaussian noise, eventually you actually get white noise. You perturb all the visual content of that image. So this forward process is usually fixed, and we're going to call it just forward diffusion process. The second process is the reverse process that starts from noise and to denoise input images one step at a time. This process is shown from right to left, so it starts from noise and goes back to data. And this process can be considered as a generative model because it starts from noise and it learns to denoise these input images one step at a time from right side to left side, right? So you basically can think of this reverse denoising process as a generative process. And this is actually going to be the parametric part where we're going to try to train to be able to train generative models and generate samples of cute cats. So maybe a little bit deeper into these two processes, we're going to assume that these processes are defined over T steps. This capital T is usually very large. It can be like 1,000 steps. And we're going to define the forward process using this Markov process. This Markov process defines the distribution of all these noisy instances. So this is x0, and here we have x1 all the way to x capital T. So it defines a joint distribution of noisy instances using this product of conditionals, each one of them defined on each sampling step. So given xt minus 1, we're going to infer a distribution over the next step. So using product, we're going to define this joint. This is just a simple Markov process. Each conditional is also simply just a normal distribution, right? So each conditional takes the sample at previous step. You can think of like this image, we will take it. We're gonna use that sample and just multiply it by this scalar. This square root of 1 minus beta t, think of it as just a scalar that takes this xt minus 1. And this usually scalar, beta t is usually very small positive value, like you can think of like 0.001. So this scalar is just less than 1. So this coefficient will just shrink the sample a little bit. And then we have this beta t here, which is again positive, very small positive value, which adds a little bit of Gaussian noise to the image, right? So at every step, we're just basically taking the sample in the previous step, we shrink it tiny bit, and we add a little bit of noise. We shrink it again, we add a bit of noise. So every step is just a very simple Gaussian perturbation kernel. You can think of it, this is diffusion kernel that diffuses the samples one step at a time. The reverse process is also a Markov process that starts from this x capital T on this side. So P of x capital T, we're going to assume that we know this distribution. So we assume that, for example, this can be represented with a normal distribution. And we design the forward process such that we actually know that any data point is eventually will be mapped to a standard, for example, normal distribution. Right? So we're going to assume that this at the end, x capital T, the normal, the distribution is normal. And then we're going to now define again Markov process that starts from samples here and then defines this joint over these denoising steps. So again, we're going to infer distribution xt minus 1, given like less noisy image, given the current input noisy image. And again, these models make a very simple assumption. They also assume that the denoising model is also Gaussian. And here, again, this Gaussian distribution takes xt as input, the current step, and predicts what is the less noisy version. And for doing this, we need the mean and the standard deviation, usually, or variance. The variance is very easy. We can just set maybe sigma t equal to beta, the same variance we use in forward process. Most of the times, we can use the same variance. However, this mean becomes the trickiest part. This is actually the part where we need to train the model, right? So this mean is actually a trainable neural network that takes current noisy image and predicts the average of less noisy version of that. And this trainable neural network, it takes an image and predicts less noisy version of that image, because the input and output have the same dimensionality. Usually the way you implement this, you would use some neural network called U-nets. They look like U because they start from image, they go like they get some low resolution feature maps, and they do upsampling to come back to the same resolution. They're also known as denoising autoencoders. So if you're not familiar with these networks, don't worry. It's just some networks that takes a noisy image and predicts less noisy version of it. So this is about diffusion models. So these are how they are defined. Maybe it's a good time for me to stop. I think this is maybe one of the most technical slides I have. So do you have any questions about diffusion models here?
Any questions? So I also want to highlight the, here, maybe you can explain that for the denoiser, there is also an input of T, right? In addition to X of T. Maybe if you could explain that.
This actually is a very good point. Yes. So this denoising model will be shared across time. So we're not going to have one model separately at each time. So we're going to actually share this model. So because the task that the model is doing here is very different than the task it's going to do here. So the model needs to know at which time step it's operating. So you're right. We actually give this time step as some form of input to the network. Usually it's done through some positional embeddings, like there are some feature maps extracted from time, and then they're passed to this neural network. So that we want to kind of make neural network be aware of which time step it's operating at. This is actually a very good one. This network will be shared across time, in most frameworks. And we will talk about like, maybe sometimes we may not want to share it. But yeah, that was actually a very good point.
Sounds good. I don't see questions from
online. I see Ming Celine is asking me a question. Ming, you can ask me actually if you like.
Could you unmute and ask your question?
Yes, I was just wondering, in terms of, we have a Gaussian distribution here, and I would imagine that the same process will work if we have a different kind of distributions. Have you tried? I mean, going both ways, forward and back.
Yeah.
I mean, this is basically a filtering process, right?
Yeah. I think so. Yeah. So I think. Yeah. Sorry.
Go ahead. Go ahead.
I think your question is, can we use other forms of distributions, right?
That's right. That's right.
Yeah. I think that's a very good point. I think there is a few works that are trying to do this. The thing is, there are a few requirements for using any other distribution. One of the requirements is that, so here we're defining the process one step at a time. Eventually, when we are training, we actually want to be able to jump over steps and directly sample from this step given the previous initialization, right? So this is usually marginalization. So for example, marginalization in Gaussian distribution is very easy, right? And I can imagine that maybe for like general, I don't know if it's exponential family distribution, it might be easy. In general, there are some requirements like being able to marginalize this Gaussian, this like perturbation process. And also we need to analytically show that at the end of process, you converge to something particular because we're going to use it in the reverse process. So there are a few requirements. If we can kind of match those requirements, I think we can easily use other distributions. And I think I've seen like some gamma distributions and things like this being used. I don't know how much in practice they make a difference, to be honest. Some of them, the improvements may not be huge.
Right. So the reason I'm asking the question is I believe there are distribution that can potentially lead to a faster convergence.
Yeah.
That may not need as many sampling steps.
Totally.
Right. That would totally change the learning process in both directions.
Yeah.
Thank you.
Yeah, totally. Yeah. I think we have one work that we call critically damped long-join diffusion, where we actually introduce additional variables like momentum type of variables to improve the convergence in the forward process. So I would actually, if you're interested, I would actually encourage you to check that work too.
Okay, will do. Thank you.
Thanks.
One more question.
Yeah.
Audience, Nathan, please go ahead.
Hello. So if I'm kind of understanding this correctly, you have like this blank canvas of like white noise, and you're kind of bringing out this generated image from it. Is that kind of how it works?
I mean, yes, white noise, exactly. You, at the beginning, you actually don't know where to go. You're going to go just towards the average direction. But yeah, eventually you learn through this stochastic process, you come back to image distribution. Yeah.
Okay, thank you.
Yeah. Okay, I'll continue and then we can pause a bit later again. So what I described in the previous slide, it was actually discrete time diffusion models where we define this forward process and reverse process in like some discretized time setting where like we said, oh, we have like 1,000 steps. You can actually present this also in a continuous time framework where now you have potentially infinite number of steps, right? And if you want to do this, you would need a framework called like a stochastic differential equation to describe these processes. These stochastic differential equations are kind of represented here from left to right as a forward diffusion process and right to left as a reverse denoising process. So you can think of these like a stochastic differential equation. What they do is the forward process, you can think of you start from this like, here I'm just showing like one-dimensional data distribution where like cats are maybe at these like dominant modes of this distribution. And you start this like random walk from some of these samples and you just go, as the time increases, you just do some random walk in this space-time, like a spatial and temporal space, and eventually your random walks converges to known distribution, right? This known distribution happens to be a standard normal distribution. So this stochastic differential equation will basically give you a framework where you can have now continuous time notation and start from distribution, do some random walks, and eventually converge to some known distribution. And the reverse of this process, now start from noise and undo this process, you're going to actually get a generative model that learns to start from just a known distribution and come back in time and generate data.
Arash, sorry to interrupt. Lost you for roughly speaking 30 seconds. If you could
30
rewind,
yeah, totally.
Pause.
Yeah, for sure. So I was saying that so these stochastic differential equations basically the forward process learns to start from data and map it to like by using these random walks, map every sample in the data distribution to some distribution in the like at the end of process, which is known. It's going to be standard normal distribution. And now if we can do the reverse of this process, the reverse process would be another ST that would start from samples from standard normal distribution and undo this forward diffusion. So it's going to the reverse process will be another STE that comes back in time. It starts from Gaussian noise and comes back in time and generates data samples. It's actually known that if you have a particular forward process, reverse process can be explained as this STE. Here, this STE says how you're going to update your samples over time. So d of x, you can think of how you're updating your sample. Here we have this drift term that consists of two terms. There is this x you can ignore for a moment, but there is this other term, which is, we call it score function. This is the derivative of log likelihood of samples at each time step. So PT is the distribution of samples at this time step. And this is just derivative of log likelihood of samples at that time step, where the derivative is with respect to x. This is known as a score function. And if we have this, we're going to be able to start from this base normal distribution and solve this STE involving this drift term and this diffusion term backward in time, and we're going to be able to generate samples. So you can think of like what I presented in the previous slide is almost identical to this STE framework, where by knowing this score function, you're going to be able to start from normal and generate a normal distribution and solve the STE backward and get data samples. And the role of this score function is almost the same as the unit I showed you in the previous slide for denoising. So this is also this score function is also implemented using units that are time dependent. And there is actually a very nice paper that got outstanding paper award at ICLR 2021 by Song et al. That they showed that you can take models that are trained in discrete time setting and convert them to these continuous time settings, or vice versa. You can actually show that the framework I showed you in this previous slide is a particular discretization of this continuous time formulation that is derived from this ST. So I'm not going to go to details of SDEs. It's just these two are equivalent, and sometimes people use score-based generative modeling to refer to these continuous times models, and denoising diffusion models to refer to discrete time setting. But in reality, these two are almost the same. The way they are described, the processes are the same. It's just one is the discretized time setting of the other one. I'm not going to go deeper beyond this. So I didn't talk about how we train these models and stuff, but if you're interested about this, I would highly encourage you to check our CVPR tutorial that was present this year at CVPR. And we have 4 or 5 hours of video where we start from very basics. We dive deep into diffusion models. We introduce how the training is done. And this actually tutorial got a lot of attention in the community. A lot of folks have been using it to when they're starting their work on this space. So I highly encourage you to check this tutorial. All the slides and the videos are available on this website. So I'm gonna present very few papers, very few projects that we've done at NVIDIA using diffusion models, and later on I'm gonna go to details of a few of them that are around sampling from diffusion models. So very recently, we introduced this framework called Edify. It's a text-to-image generative model that uses ensemble of now expert denoisers. So you remember earlier, Sohail was asking me, how do you do this like time dependency, right? So I was telling you that usually these diffusion models, they use this denoising framework, this UNet that is shared across time. So in this paper, we actually observed that when you have this like a stochastic process, for example, starting from noise and coming back to data distribution, this is going to be text to image generative model, right? So we take a text and we want to generate an image that corresponds to this text. What we notice is that this model actually has access to 2 sources of information during sampling. One is the input text, and other thing is the input noisy image that is trying to use to infer the less noisy image, right? It turned out that at the beginning of the sampling, when the input is pure noise, actually this text input plays a key role. So the network uses this text mostly to infer what is the direction that it needs to go to denoise the image. But as we form the image, when we have some of the visual details formed in this process, what happens is that the denoising model starts ignoring text. And it starts using only the visual content to infer what is the less noisy version. So in this paper, we propose actually just to use separate neural networks for each one of these stages rather than sharing parameters. Now we're actually going opposite direction where we're using separate networks. The nice thing about this approach is that now we actually don't need to the nice thing is we actually don't increase the computational complexity at the sampling time, because at the end of the day, you're going to use a network at each step. So we're just replacing that network with other parameters. However, this introduces additional challenges, mostly in training, because now you have more networks to train. So we came up with an approach for training these like ensemble of experts all together. And one thing I forgot to mention is actually the first author of this happens to be Yogesh, who did his PhD in University of Maryland under Sohail and Professor Rama Chalepa. And actually, I think this is one of the first projects that Yogesh did at NVIDIA. So I think he's very proud of this project. And I'm really happy to see that actually the alumni from University of Maryland are doing such a great work with us here. So no, this was one of his first projects that actually is very key. And
this is very interesting. Of course, Yogesh is amazing. Just one quick question. Yeah. So this is very interesting. Can you even combine these 2 approaches? Maybe like for some part of like the, especially in the reverse part, maybe at the beginning, you can basically share a lot of parameters. You can use a UNet, but maybe towards the end, you can use expert denoiser to have higher quality generation.
Actually, so you make a really good point. So what we end up doing is not necessarily each time is separate. It's like intervals of time. We're using one model. So you're actually thinking of a very good direction, because we end up actually observing that there are kind of 3 models play key role. One is models at the very beginning that mostly rely on text, models in middle that are kind of disambiguating, and models at the end that become specialized at denoising. So it's actually kind of, as you said, it's actually a hybrid approach where in this, we split the continuous time into these intervals, and then the model is shared in those continuous time subsets, kind of. And one of the best working version was basically this like three models that are especially at different stages.
Great, thanks.
So here we're comparing actually Edify to some of the publicly available text-to-image models, including Stable Diffusion, DALL-E 2. And you can see that actually Edify can basically represent our motto that NVIDIA rocks, and can put this on t-shirt of a nice little puppy. We can also see that not only we can generate dogs, we can even cats that are riding scooters, and they have a bandana, and even they have a helmet, like a biking helmet on them. And these are really nice results that we get from Edify. One of the new things that we introduced at Edify was also this paint by words, where we let artist or user to, I was sorry, show the video again. User can just paint a rough sketch of the scene that they like to see. Like they give a sentence and they say where they think each object should be. And then the model uses this rough sketch to generate the image that corresponds to that. And we can even make squirrels fight in a bar with the gloves in different colors by just drawing the sketch. Another work that I wanted to briefly highlight is this framework that we're going to present at NeurIPS this year. It's called LINE, Latent Point Diffusion Models for 3D Shape Generation. What we want to do here, we want to train diffusion models to generate 3D point clouds, right? So point clouds are the most basic form of representing 3D objects. So here we came up with a framework that not only generates point clouds, but it also uses some off-the-shelf surface reconstruction algorithm to convert these point clouds to very nice meshes. Basically, now we can generate not only point clouds, but also the meshes using this framework. And this is another result on 55 categories from ShapeNet. ShapeNet is a known benchmark in this space. However, we're not aware of previous works that have been trained on all 55 categories. It's a very challenging task to train unconditional models on all these 55 categories. And we showed that actually this framework works very well in this task. This framework uses latent diffusion models in the core, which I will discuss a bit later in this talk. The third work that I wanted to highlight is this work we call DiffPure, diffusion models for adversarial purification. So the goal of this work is targeted for adversarial purification or adversarial robustness through purification methods. So you've probably, I think, Sohail, you covered this in your course, adversarial robustness algorithm. So we may have application where we have adversarial image, for example, this image of panda where there's a little bit of very low level perturbations that are not visible to human eye. These perturbations are on the pixel values. And because of this perturbation, if you give this image to another classifier, this classifier may not be able to classify this as a correct panda class. So what we do in this project, we actually show that we can take this adversarially perturbed image and add a bit of Gaussian noise by following the forward process. So we take this adversarial image, add a bit of noise by following Gaussian process, the forward process, and then we don't go all the way to the end. We don't map it all the way to pure noise. We just go a little bit forward. And then we use this reverse generative SDE to convert this noisy image, the intermediate step, back to a clean image. And what we argue is that adding this noise actually not only just adds a little bit of noise, it also washes out all these small perturbations that are introduced because of adversarial perturbation. And then this reverse denoising process basically gets rid of all of them. And it gives you a clean image that if you now give it to a classifier, the classifier is less likely to be misled to a different category, right? So this is called adversarial purification because you're just using a generative model to purify input image from any adversarial perturbations. And the nice thing about actually using a generative model for this task is that we're not training the generative model for particular adversarial attack. So the model is not aware of what would be used at the test time to attack this framework. We're also not modifying any classifier. So it can be actually, you can just take a generative model like this, like diffusion models, and just define this diff pure process and plug it to any classifier. We're not training the classifier using, like, for example, adversarial training that is usually used in the community. So one challenge is here is how to attack this framework. And so in this paper, we discuss how we can basically backpropagate through these processes. So actually there are well-known works where they show how you can backpropagate through STEs. And we use those techniques to attack this framework in an end-to-end fashion. So here I'm going to show you some example on the left side. I do hope that you can see these examples well over your project. So here on the left side, we have these adversarially perturbed images, and we intentionally increase the magnitude of adversarial perturbation so that they're visible to human eye. So here we take these examples as input and we add noise by following the forward process. And then here I'm showing you what would happen as we are denoising using a generative model. So at the end, we get these clean images that, as you can see, they don't have these adversarial perturbations that were present in the input image. They're also very similar to the clean image corresponding to them. So this process does not necessarily change the semantics in the image. And then we can use this output and pass it to classifier for the final classification. We compared diffpure to several works that are designed for handling unseen threat models. And we saw that actually these purification techniques using diffusion models can do very well compared to some of these state-of-the-art methods. And we believe that there might be a very good potential for diffusion models to be used for adversarial purification. This work, I think, started some excitement in this space, and there has been multiple follow-ups analyzing this purification technique. So given this, I want to now switch gear a little bit and start discussing 3 works that we have done recently on accelerating sampling from diffusion models. As I mentioned, I will focus mostly on latent score-based generative models or latent diffusion models and denoising diffusion GANs and higher order solvers for diffusion models. So if you remember at the beginning of the talk, I mentioned that there are these stochastic differential equations that map data to some known distribution, and then the reverse of them becomes a generative model. What happens is that when your data space is highly multimodal and you use these STs to map them to noise, these STs, actually the reverse generative STs, become actually very complex because they start from very simple distribution and they're going to map that distribution to very complex multimodal distribution, right? So because these STEs have a very complex dynamics, solving them numerically can be very slow. So if you want to simulate them and solve this STE numerically, you end up actually using thousands of steps. And this is one of the reasons why sampling from diffusion models is slow, because these STEs that emerge in diffusion models can be actually very complex and very slow to solve numerically. So given this challenge in diffusion models, we were asking ourselves, okay, so how can we compare diffusion models to other known generative models in terms of 3 criteria, in terms of fast sampling, mode coverage or diversity, and sample quality. What we noticed that generative adversarial network tend to do very fast sampling and they tend to generate very high quality samples. But in terms of mode coverage, they do poorly. Usually they miss modes and they may not be able to represent all the diversity present in your training data distribution. On the other hand, likelihood-based models, including variational autoencoders and normalizing flows, especially when they're applied to images, they tend to generate samples fast. They do very well mode coverage in terms of mode coverage. However, sometimes they lack quality. It's very challenging to get high quality samples from likelihood-based generative models defined using VAEs and normalizing flows. But if you look at diffusion models do very well on these 2 tasks. Like they do very well at mode coverage. We have very good evidence that they cover modes. They also do very well in terms of sample quality. However, their sampling from them can be very slow. And this is a limiting factor. Anytime you want to, for example, have interactive tool where some artist likes to interact with your generative model, it's going to be very hard. Artist needs to just click on something, go take a walk, and come back to see the results. Right? So one of the goals we want to achieve here is to address this trilemma. We call it generative learning trilemma because we don't see frameworks being able to address all three at the same time. And what we want to do, we want to be able to tackle this trilemma by accelerating diffusion models so that we cover all three criteria. So one of the works that we did, we actually showed how we can potentially train score-based generative models in latent space. This is a work that we presented last year at NeurIPS. So as the name suggests, I think you could probably guess that what we are trying to do here, we just simply want to use a variational autoencoder. So here on the left side, you see variational autoencoder. It consists of encoder and decoder. Encoder takes input image X, maps it to some latent space using some encoding distribution, and a decoder that takes samples from the latent space and learns to decode them. So this is just a generic variational autoencoder. The main difference is that now we're going to assume that our latent distribution, our prior distribution over latent variables is defined by a score-based prior or a diffusion model equality. So we're going to assume that we have a diffusion model in the latent space that represents the prior over the latent variables. So again, the idea is very simple. We use just an encoder to map the input data to some latent space, and then we just form the diffusion model in that latent space. The reason we may want to do this, we actually foresee that there are three advantages to this. One is that we know that do you have, is there a question? Sorry.
No.
Maybe it was echo. Yeah. So we know that a VAE can map this complex data distribution in the latent space to much simpler distribution. Right? When we train VAEs, we're actually encouraging the latent embeddings to be as close as possible to normal distribution. If VAEs can do this, we would be done. If the encoding distribution is perfectly normal, we would be using VAEs for everything. However, there is always a bit of mismatch. The distribution comes close to normal, but it's not exactly normal, right? But however, we know that if the diffusion model is operating on a space where the samples have no distribution very close to normal, these mappings between the latent variables and this normal distribution will be a very simple, smooth mapping. And because this mapping is very simple, then the SDEs that will emerge, differential equations that would emerge, will have very smooth functions that their integration can be done very easily. Numerical integration can be done very easily. So one idea is map the complex data space to some smooth distribution such that diffusion models can represent easily. The second idea is that actually, second advantage is that now you have some form of augmentation happening in your space. So by adding more auxiliary variables into your space, you actually introduce expressivity into your generative model, which is a known fact in generative learning community. And the last advantage that we can see is that we can now potentially use these latent diffusion models and apply them to type of data that we previously could not use for diffusion models. Like, for example, if you have graph data or discrete text data or 3D data, now you can use autoencoders to map this input space to some latent space that is continuous and just apply diffusion model there. So it gives some flexibility as well in terms of like what kind of data you can apply diffusion models to. So for training this model, our objective is very similar to variational autoencoder objective. This is just variational lower bound that I have here. Variational lower bound, if you're familiar with it, it consists of two terms, the reconstruction term and the KL term. The KL term can be easily decomposed into entropy term and cross entropy term. And what happens in our framework is that the first two terms are basically identical to the terms that you see in VAEs. The reconstruction term and entropy term can be easily approximated, for example, using reparameterization trick that you might be familiar in VAEs literature. However, the only tricky term that we need to optimize is this cross entropy term, because it's defined from this encoding distribution to this distribution is defined through this diffusion process. Okay, so this is the trickiest term. And in this field, one of the technical novelties that we had was that we showed that actually how you can express this cross-entropy term using a very simple objective known as denoising score matching objective as used for training diffusion models. So we actually showed cross-entropy can be easily expressed using this denoising score matching objective. This objective by nature is also very high variance. We also came up with several techniques for reducing the gradient of the objective using importance sampling. So we came up with some importance sampling techniques that reduces the variance of this denoising score matching objective used for cross-entropy. It might be a good idea for me to pause here and let you ask me a question about latent score-based models.
Okay, sounds good. Any questions so far? I know there was a question at the back. We didn't have time. Do you want to? Yeah, so Arash, I'm not sure if you heard the question or
I didn't. Can you please repeat? I couldn't hear very well.
we have the ceiling microphones, but some of them they're not working. So I'll repeat the question.
Thanks a lot. Thanks.
The question is that how can we know that diffusion models don't memorize training samples? Especially, basically, the question was contrasting that with GANs, where the generator, doesn't have direct access to the training samples, while we in the diffusion model, we do have such an access.
Yeah, this is actually a very good question. So the reason we can actually claim such like, oh, they do very well in mod coverage and they don't necessarily overfit is we can measure test log likelihood using diffusion models. So we can actually have a whole data set and measure log likelihood of the model for that data set. And we see that actually we don't see any sign of overfitting. Like in terms of like log likelihood does not go up. I mean, if you have a very expressive model, you may see that, oh, diffusion models are starting to overfit and log likelihood may start going up, but there's simple regularization techniques that are helping. One of the very first papers that made diffusion models very popular actually measured log likelihood as well, and there was no sign of overfitting. And this is a very nice thing about diffusion models because we can measure log likelihood as well. Whereas like GANs, it's extremely challenging to measure log likelihood.
Sounds good. Any other questions? I don't see any questions, so we can go ahead.
Okay. So these are some of the results that we got with latent score-based generative model, or latent diffusion model on these 4 data sets: CFARTN, Celebay HQ, MNIST, and Omniglot. This video shows latent interpolation in LSGM. So we're basically walking in the latent space, and this is actually the base normal, standard normal distribution that we are walking at. Then we're just solving the reverse process, and then we're decoding images as we're walking. I know that over internet connection, this might look choppy, but actually this is also choppy even on my end, because what happens is that you actually see, as you're doing interpolation on these models, you see actually a sharp transition usually. I will go back and show there's sometimes sharp transition from one object to another, for example, CFARTN, or some like face to another similar face. And the reason for this is that actually, this is kind of a nice feature. It's not a bug in these models, is that, the data distribution kind of consists of many islands, especially in like this kind of CFARTN type of data set where you have like 10 different categories. You can think of like there are just like islands in the data space. And when you fit this diffusion model, it covers all the islands, but there are gaps in between them. So as you're walking in the base distribution, you may all of a sudden jump from one island to another. And these sharp transitions kind of represent that. And this is one of the reasons why diffusion models are good. Other techniques cannot handle this. Other VAEs and GANs, GANs drop modes. So they only represent a few modes very well, and they just ignore the other islands. VAEs cover all the islands. However, there are gaps in between them. They also can sample a lot from these areas between islands, right? So, and this is very nice about diffusion models that can learn this complex data distribution so well. This is how it would look like as you are solving the reverse diffusion process in the latent space and keep decoding the samples. So you can see that we start from these like very cropped images and come back to clean images. However, one thing you see that there is no noise on these images, right? This is because the reverse process is happening in the latent space. So the dynamic that you observe in the data space is very different. It's not the same as what you would see in the diffusion models applied in the data space. As I promised you, like one of the main reasons why we want to come up with latent score-based generative model was accelerating sampling. So at the time when we were doing this paper, we compared our method on celeb-A dataset to this paper that I mentioned to you that got best paper award at ICR 2021. They used this sampling technique called predicted corrector that involved 4,000 network calls. When we run this on a batch of, I think, 128 images, if I remember correctly, the batch size, it took us 45 minutes to do one batch sampling. And compared to our method that required only 23 network calls done in 4 seconds, we got around 700 speed up by doing our sampling in the latent space. And there are multiple reasons why we could actually get huge speed up by doing sampling in the latent space. One is that our latent space diffusion is much smaller than the data space diffusion. Right? The latent space, we have 32 by 32 spatially arranged latent variables, whereas data space, they are operating at 256 by 256 images. So our network is much smaller. It's much shallower because the spatial resolution of latent variables is smaller. Secondly, we know that the latent distribution of our latent variables in our latent space is much smoother. It's closer to normal. And as a result, the STs and ODs that are formed in the latent space, differential equation formed in the latent space, are much smoother and easier to solve numerically. So we don't need a lot of functional evaluations. And finally, because we're doing everything in the latent space and we're using a decoder finally to map the latent variables to data space, what happens is that if your prior makes mistakes, decoder can fix some of those mistakes. You know, if there are some like perturbations in the latent space because of, for example, numerical errors, your decoder might be a little bit robust to that because you're using a neural network to sample to generate the data eventually. Whereas when you have a diffusion model directly in the data space, any artifacts in sampling will basically translate to visual artifacts that you will see because there is no correction module at the end. So just to summarize very quickly, we introduced this framework called LSTM that embeds data into some smooth latent space and models the distribution of latent variables using score-based priors. LSTM has 3 advantages. One is expressivity of the models is increased. Another one is the sampling speed, because we can form diffusion models in a smaller space and a smoother space. We can actually get samples faster. And if you have heard of latent diffusion models or stable diffusion that is built on top of this, this paper was originally proposed at CVPR 2022 by Robin Rambach et al. And what they actually observed, this came 9 months after our paper, but they actually show how you can take these models, train them at very large scale, and using some very nice actually kind of engineering tricks, they show that you can train these models. And because you're forming a diffusion model in this latent space, very low dimensional latent space, sampling time from these models can be very fast because the dimensionality of the tensors that they're operating at or input that they're operating at is much smaller. So we kind of predicted this originally at LSTM, that's why latent diffusion models can be very successful. We also predicted that you're going to be able to apply diffusion models to non-image data easily, as long as you have some autoencoder that takes your data, maps it to some latent space. And we ourselves did it for 3D point clouds, but we also later saw works on, for example, applying diffusion models to language models, where the language by nature is discrete. So they use some very simple encoder decoder to map discrete data to continuous space and define the diffusion in that space. This brings me to the second part, where I would talk about denoising diffusion GANs. Maybe before we start, Soil, you mentioned that you have the room a bit longer. How much should I go over time? Is that okay, or it's not a good idea?
If you can, we have the room for 20 more minutes. So
20 more minutes. Okay. I think I will put maybe 10 more minutes maximum, and then 10 more minutes maybe at the end for discussion or something. If that's
that sounds great.
Okay. Okay. So the second work I want to mention is this work called Denoising Diffusion GANs that was presented this year at ICLR. So if you remember, in the previous part, I talked about how we can map the data to latent space and sample from it faster using diffusion models. Here, we're not going to go to latent space. We're going to stick to data space. And we're going to ask ourselves, what would happen if we didn't denoise for a smaller step? We try to denoise for much larger steps, right? So this is, if you want to reduce number of functional evaluations, one thing is that start from here and try to jump over multiple steps and denoise for larger steps. It turns out that if you have a distribution, here in the top, I'm showing you this one-dimensional distribution. This is the data distribution, and these are all the marginal distribution that are formed as you're diffusing, right? So the top part, you have this one-dimensional data distribution, and these are a smooth version of that distribution that is formed as you're diffusing the distribution. These are like a marginal data distribution at these time steps. If you have some sample in the intermediate step and you want to denoise, if you're denoising for a smaller step, your denoising model is actually a normal. Here in yellow, you can see, sorry, it moves too much, too fast. But when you see yellow curve, you see that actually it's mostly normal. But as you're trying to denoise for larger step, this denoising model starts being not normal. It becomes kind of bimodal. It starts having actually complex multimodality as you're trying to denoise for larger step. So basically what we observe is that if you want to denoise for a very small step, this normal assumption that is used in denoising diffusion models, it holds. But if you want to denoise for a very large step, you have multimodality in the denoising, and that normal assumption would break. So in this paper, we just propose something very simple. We say, okay, this normal assumption holds for very small denoising steps, and that is the reason why you need to keep doing it many, many times to be able to generate image starting from noise. But if you want to jump over these steps, you actually need this highly multimodal denoising model, right? So if you want to just do in 2 steps, you will start from here, you will come to this intermediate step and then denoise it in another step. But each one of these steps would require multimodal distributions. And in this paper, we just simply suggest, let's use conditional GANs to mimic each one of these denoising models. So this is kind of a hybrid framework where we're still diffusing data and we're learning to denoise it. However, each denoising is represented using conditional GAN rather than the normal distribution. So here you can see our results on C410 dataset on the right side. And here on the left side, you see that the FID, which is a representative of quality versus sampling time trade-off. Ideally, we want to be here where we have good low FID, which is represented high quality, and low sampling time. And you can see that our framework shown in purple actually gets almost 40x speed up compared to some of the fastest diffusion models while having very similar sample quality. And this is basically because we don't need to do many functional evaluations when we're denoising. We can just call GAN multiple times. Here, we're trying to compare our several models against these 3 axes. One is sample quality measured in FID, so lower towards the center is better. Sampling time towards the center again is better. And 1 minus recall, you can think of recall represents the diversity or the mode coverage, and 1 minus recall, the lower would be better, right? You will have better mode coverage. So here we're comparing our model, the denoising diffusion GAN, to style GAN, which is one of the best GANs that was out at least when we were doing this work. DDPM and DDIM. There are 2 different. DDPM is the original denoising diffusion model by Jonathan Ho, and DDIM is a faster version of it. So we compare our models to these works, and you can see, for example, DDPM shown in blue here it has a very slow sampling time. It has very good FID, good sample quality, very good mode coverage in terms of recall score, lower is better. Then we have style GAN that does very good sample quality. It is very fast compared to DDPM, but it has very poor mode coverage. And then we have, for example, ours here in middle, this green triangle, where we kind of can get balanced improvement of all sampling, mode coverage, and sample quality at the same time. So this is why we call our framework tackling the generative learning trilemma, because we're trying to tackle all these three criteria at the same time using denoising diffusion GANs. These are the results that we saw on Celebi HQ 256, as well as Elson Churches. And I think looking back, comparing our denoising diffusion GAN that came after latent space diffusion model, we actually see a very nice trend on Celebi HQ. We see that we almost kept the FID the same. However, we could reduce the number of function calls. Like from 4,000, we went to 23, and then we went to almost 2. And eventually, the ultimate goal is to get to 1 function call, like keep the same sample quality, same mode coverage, and hopefully get get the same sampling generation in just 1 function call. So this part, I briefly introduced denoising diffusion GANs, and we argue that these models can generate samples faster. They have better mode coverage compared to conventional GANs. I didn't discuss that. Compared to conventional GANs that generate samples in 1 step, these models tend to have better mode coverage, and we also have a high sample quality. If you're interested in playing with this, I would encourage you to check our project page here. Maybe we can take 1 question before just talk about the third work very quickly too.
Any questions? I don't see any questions. Maybe we'll, we can talk about the last part, and then we can do a more extensive Q&A.
That sounds good. Yeah, this part I will keep it short too. So this is a work that we will present at NeurIPS in few weeks. It's called GENIE. We find the acronym through some letters in middle of this higher order denoising diffusion solvers. We just like to call it GENIE. So if you remember at the beginning of talk, I was telling you how these continuous time diffusion models can be explained or can be described using stochastic differential equations, right? So at the beginning of talk, I was saying, yeah, we can define these random walks. You can think that they start from data distribution and they converge to normal distribution, and they can walk back to generate data. What I didn't tell you earlier was that there's also equivalent ordinary differential equations that also define very similar mapping from noise to data distribution, with the main difference that these mappings are not deterministic, right? So you can basically use diffusion models, train them. At the sampling time, you could potentially use these stochastic differential equations that generate samples by just, you have to solve these stochastic differential equations to generate data. You can also just take the same model and formulate ODE, and ODE, ordinary differential equation, that also starts from the space normal distribution and converts samples to samples from data distribution. This is really nice because ODEs have been around for a very long time in different areas of science. They are well studied, and there are just so many different solvers you can use to access sampling from ODEs. And it turns out actually, if you want to go to extreme of very few function evaluations, these ODEs can be they can get very promising results, because it's just much easier to solve ODEs with large step size compared to SDEs. So in this work, we're going to introduce an ODE solver that we specifically designed for solving diffusion models. Here, I'm expressing ODE that we're going to solve at sampling them in a very simple form. So we just use this dx, where this dx depends on this temporal dynamics represented by this E theta that takes x and t again. And we're going to assume that we're going to represent this ODE through these mappings that start from deterministic mappings that start from known Gaussian distribution that are mapped to data distribution. If you want to solve this ODE, the simplest thing you can do is just you can use the first order, first truncated Taylor method, which is basically the Euler method that What it does, it just simply, this function that you're trying to integrate over time, you're going to just have a linear approximation of this function. And given this data point, you say, where would this function land at after taking delta t? So this trajectory, you just approximate using some linear function, and you predict where that trajectory will be at delta t. You can make your approximation more accurate by taking higher order Taylor method approximation, right? So if you use now second truncated Taylor method, you're going to approximate this function locally using a quadratic function, and you're going to be able to have a better approximation of this trajectory as you take delta t. It turns out that the first truncated Taylor method is very simple to do, and that's what most of the papers in the literature also use, that they basically, you take current xt and you evaluate your function, and you just add that to current xt with some rescaling that depends on the step size, basically, right? For second Taylor method, you now need this higher order derivatives that we don't necessarily have access to that easily, right? So we have this derivative of the function that we're integrating with respect to dt. And what we propose in this paper is that you can just simply use a neural network to approximate this term here, this higher order derivative. So at the sampling time, you can easily have both approximation of this term as well as this term with very low computational, basically, cost. You can get both of them. So Gini is all about approximating the second order derivative using a neural network directly, so that you have both first order derivative and the second order derivative at the same time, using the same kind of computational budget. So if you remember, originally I said that the ultimate goal is to generate high quality cats. So finally, we can actually present a model that has been trained on cats, and it can generate very high quality samples of cats. And here, because we're using Gini, actually this process can be done much faster, the sampling generation. So I will just show you again. There might be some cat lovers in the audience. If we compare Gini to other sampling techniques, again, this is FID versus sampling, number of function calls for sampling. And you see that Gini, which is an ODE solver, compared to other ODE solvers, gets most of times better FID with the same number of function evaluations. These are other either ODE or sometimes SDE solvers that have been proposed in the literature. Before ending the talk, I just want to ask, I want to just say thank you to all my collaborators and colleagues and interns. I've been lucky to work with a lot of research directors and VPs, including my boss, Jan Kutz, and Anima and Akuma, Mingyu, and Sanya. Also a lot of colleagues, including Karsten, Weili, Yogesh, Sungjun, and amazing interns that I was lucky to work with, Tim, Shaohui, and Zhisheng, whose work actually were highlighted at different parts of this talk. So with this in mind, we can stop and take more questions.
Okay, thank you, Arash. Looks like Arash for such a great talk. We have time for some questions. And Zoom audience, if you have questions, you can raise your hand. Arash, so let me ask you maybe one or two questions that I have in mind. One is that, I think you mentioned that one advantage of diffusion model, we have access to the log likelihood function, right? So we have that in the normalizing flows, but we don't have it in GANs. In normalizing flows, we had a lecture on that.
Yeah.
And basically, we were also discussing that sometimes if you train a normalizing flow on a data set like CFAR, and then you look at the histograms of the log likelihoods of another data set, then you may, sometimes get presumably some strange behaviors. For instance, MNIST, likelihood distribution can be higher on average than the ones that you have used in training, and there are some justifications for that. But I want to see, have you looked into this, for diffusion models? And if so, do we see, roughly speaking, similar behaviors?
Do you mean like if we take some other data sets and measure log likelihood on the diffusion models and what we will see?
Yes.
I see. So I think, yeah, that's actually interesting. Yeah, that's one of the reasons why we cannot use log likelihood based models for, out of distribution detection, because technically for out of distribution detection, they should be able to give some like low likelihood, like for out of distribution samples. I haven't looked at it exactly for out of distribution detection. However, what I've seen is that what happens is, you remember we're diffusing the samples, right? And we are learning to denoise. If you measure like kind of bits per dimension, like log likelihood per time step, some notion of that, you would notice that a lot of log likelihood is paid at the very low time steps when the model focuses a lot on small details, right? So if, for example, you want to train a diffusion model specifically for log likelihood, training, you would actually give very high weight for small t's, because you want to kind of, your model should be very special to these very small t's, because most of the log likelihood cost is paid there. Whereas at high t's, you're not going to pay that much log likelihood. Whereas these high t's are where these like very coarse level information is perturbed. Like we have some discussions we actually discussed this in the tutorial a little bit, but you can think of like as you're diffusing, first you get rid of high frequency content, and later at the end of process, you get rid of the low frequency content. And it turns out the human eye, for example, cares about the low frequency content, and the high frequency content we cannot see sometimes, even like it's just so high frequency. So long story short, I think we could potentially train diffusion models with not log likelihood weighting, like where we actually give most results that we are seeing are actually not with log likelihood weighting. We're kind of weighting the larger steps more. And I can imagine that these models would be more sensitive to out of distribution, because they're not looking at more coarse level information rather than a very low level. But you're making a really good point. Like, it's really amazing that like diffusion models, you can think of, because when I was talking about neural ODE version, this is basically the same as continuous time normalizing flows or continuous normalizing flows, but they're just trained with a different objective. And it turns out that this objective is the key. Like the instead of like maximizing log likelihood on the whole trajectory, this reweighting plays a key role here.
Fantastic. Thanks a lot for that explanations. Any other questions? There is one question. Yes, please go ahead.
So as specifically the trilemma, so I was kind of curious of like changing the number of network calls with the GAN, but it goes to a model or something like that. So is that like basically network calls correspond to the recall that was there.
So if I understand your question, you're saying that the number of network calls, if it is a function of what?
Basically, does like the number of network calls correspond to the recall?
I see. So basically, the question is that if the number of network calls correspond to the recall that you mentioned.
Actually, it corresponds to sampling time. So recall is something different. So recall is a metric, because we cannot measure log likelihoods, right? And so recall is not the same as like number of calls. So here the sampling time represents the number of function calls. However, this recall here, what we mean is if we train a distribution and then use if you train a generative model and you use this generative model and try to see how many of your training data you can recall, which is a representative of how much mode coverage you can do, right? So this recall metric is something that was invented in the GAN community to capture diversity or mode coverage. And the primary reason that why we would use this for mode coverage is because GANs we cannot measure log likelihood for GANs. We could do for all the other frameworks, we could measure log likelihood, but for GANs we couldn't. So that's why we use this metric, so that we can compare our method against GANs for mode coverage. So this is the same as number of function calls.
Sounds good. Yes, go ahead.
So in the LLVM slide, the latent model can also handle text. I was wondering how some of the assumptions we made for this also works for text. For example, how we diffuse a variable length segment, and also what the kind of length of after before process where the flow x equals to x0 the image case actually was just an image, but here the actual variable.
Okay, so I'll just recap the question. Let's GM. Basically, the question is about, okay, so how this can be used for text, especially some of these conditional distributions can be characterized differently for images versus text.
Yeah, this is a very good question. So for text, we definitely need to use the fact that text is sequential, right? So there are a few things. I think if I remember this, if I remember correctly, this diffusion language model actually it just maps every word to continuous space and defines the diffusion on the words, like the continuous representation of words in a sentence. But we recently did a work where we actually, what we said we're going to use still autoregressive models, like, you know, masked transformers to represent sentences. You know, like these models do very well at sentence level, right? If I ask you to generate sentences with transformers, they do really well sentence level, but sometimes on the, you know, whole text level or paragraph level, sometimes their topic or content drifts, kind of, right? So what we did, we kind of came up with a hybrid approach where we said we're going to represent each sentence with a latent variable, and then this way each sentence latent variable, the whole text is just a collection of latent variables, and we're going to represent the joint distribution of all this with the diffusion model. But then given this, we're going to generate sentences using autoregressive models. So that's a nice thing about, I think, generative learning, where you can just combine models. So if you believe autoregressive models are good at low-level word conditioning, you can use that, but you can combine this with some latent variable to represent the topic of a sentence or paragraph, for example, and represent the joint distribution of them using diffusion models.
All right. Okay, so one last question, Mazda. Let's make it quick. Oh, 3 parts.
Wow.
I'll let you choose which question you want. So my first question is, what's the catch? Like, it sounds like this idea that has been around for some time. Why is it these decision? Another question is about the data requirements for training and my last question is specific to the edify. So and maybe broader about trying to understand, interpreting how these models learn this training algorithms. So basically, my question is, what's the difference in the expert? The experts and the other experts. Do you have any interpretation as to what they're doing?
So Arash, did you hear it, or should I repeat?
Please repeat. It was like volume was going up and down in the yeah.
So I think the first question is, what is the catch that, you know, the diffusion models have been around for a while, but why we see them to be very successful most recently? And basically the second question, which is related to the first one, is that, like, what are the requirements for the data in order to successfully train some of these diffusion models? And the third question was about the EDIF model. And, you know, Mazda, can you repeat? It was about.
So one is, do we have any notion of interpreting how these models work? And second, is there any, noticeable difference in what the different experts do?
Yeah, for the interpretation of these models and, you know, what different experts they rely on in their reconstruction.
Okay. So the third question has also 2 parts. That's kind of interesting. Okay, the first question, what is the catch? I read the 2015 paper that originally came, and honestly, in 2015, when I was doing VAEs back then, and it was hard to believe that a model requiring 1,000 steps would be ever used for anything. It was a bit scary, and that was a kind of a small paper in a smaller scale that wasn't like super convincing that everyone should be doing this. What happened was that DDPM paper, I think, changed everything, because all of a sudden DDPM paper in 2020 showed that with right architecture design and enough patience for training these models, and I think right parameterization of neural networks. So it kind of boiled down a little bit to parameterization of the neural network and network design, where now we had attention layers, we had very good CNNs that in 2020, all of a sudden, this DDPM paper actually showed that we can get very good results using diffusion models. I think that's what it took. Like it took community 5 years to realize that you need very good architecture and good parameterization. I think maybe the catch is that now after that people figured out how to make them faster as well. I think original DDPM when it came also people were a bit skeptical that no one would use them if you record 1,000 function calls. But then gradually also we figured out how we can make these things faster, like as a community. The second question is, what are the requirements for data? Diffusion models assume that you have continuous data, so it's not as very easy right away to apply to discrete data. However, there's also now several works that are defining diffusion processes over discrete spaces, so it's not really very hard to do this. But the original assumption was that it's continuous. Sometimes some data where you have like invariances, for example, graphs, you can take the data and they rotate it and it's the same data point, right? So defining a diffusion process on this data space becomes tricky, but there are also people who are looking into defining diffusion spaces in this kind of like diffusion process in this kind of spaces that can be represented by like manifolds and stuff usually. So there are some assumptions like this. I think one is continuous. One is whether you have invariance or not. I think if it's manifold, for example, you can represent that diffusion process in the manifold. Being discrete is also one of the challenges, but there are also diffusion models for discrete data as well. Oh, third question, Edify. So it was, I forgot the exact question. So how these models are relying on different cues, right? Different input, I think the question was, the first question.
I think it was, about the experts, what they are, relying, what is the interpretation?
Yeah. So we looked at attention maps, at least the first question. We looked at attention maps of these, each one of the denoising models, and we're seeing a very interesting dynamic where initially attention maps are firing kind of on text, whereas later on, and they don't really fire much on the visual content. And for small t's, when most of the visual content is generated, the denoising model starts attending a lot on these like local areas, and it ignores text. So this is how we know there is a dynamic happening. So usually by visualizing attention maps. We also did a few experiments where we swap. For example, we generated the image and halfway through we swapped the text and we looked at whether it's going to change the image that is generating. And we saw that it completely ignored the swapped text. Like there are this kind of things we observed that made us believe that there is a dynamic happening. What was the second part of that question?
I think he's, he looks happy. So he's
okay.
Arash, thank you so much. This has been a wonderful talk. I see there are other questions. It's a sign of a great talk because, it stimulates a lot of interesting conversations. Let's thank Arash one more time.
Thanks.